This lecture is about energy resource management in relation to the fabric of buildings, embodied energy, in other words. It is also about how badly this has been managed in the modern period compared to previous ages of architecture. I'm going to compare two buildings, the Baths of Caracalla in Rome to represent the pre-modern age, and the Riverside Museum in Glasgow, a prominent recent building. I'm going to use the concept of structural archetypes as a means of judging how efficiently the material that constitutes the main bulk of each building has been used. One of the characteristics of the architecture of the modern period, and particularly that of recent decades, has been an almost complete neglect of the idea of energy conservation in the making of the fabric of buildings. This was a luxury that could not be afforded in pre-modern times, and can no longer be afforded in the present day. As I demonstrated in the presentation Introduction to Structural Archetypes, the efficiency with which material is used in a structure is almost entirely dependent on all aspects of its form. The overall form determines the types and magnitudes of the internal forces that will occur, and the detailed aspects of form, the longitudinal profile, and the shapes of the cross-sections of the elements determine the efficiency with which the internal forces can be resisted. These ideas provide a basis for judging the extent to which the fabric of any structure, and this includes the structures that support buildings, has been provided with economy of means, a necessary condition for the production of architecture that meets the needs of low embodied carbon and environmental sustainability. I discussed this in a previous presentation in the series on structural archetypes, in which I used these images. The idea of the structural archetype can be used for several forms of appraisal, including the making of an assessment of the purely technical forms of a structure, the interpretation of the degree of interaction that has occurred between architectural and structural design, and the assessment of specific technical properties of the structure, such as its carbon footprint. These ideas can be applied to structure from any period, and in this lecture I'm going to make a comparison between these two famous buildings, one historic and the other recent. The lecture will discuss, amongst other things, the significant ways in which attitudes to resource management in a historic period differed from those of the modern age. I believe that there is much that can be learned from the study of historic structures concerning how we can move forward in the present day to the creation of a low-carbon architecture. The concepts of form action and improvement and of building for economy of means are significant aids in this quest. The idea of building with economy of means is not new. Long before the issues associated with climate change became a major concern, the designers of buildings and other infrastructure were conscious of the need not to waste the resources of the societies that they served by producing designs that required excessive quantities of material and constructional effort. Their reasons were various, but mostly it was simply out of necessity, because the resources available to build a structure were scarce and therefore precious, as we'll see with the Baths of Caracalla. This was normal in antiquity, and a concern that was expressed in the Roman treatise by Vitruvius. It also featured in the works of the Italian Renaissance, with scholars such as Alberti and Palladio, and has in fact been an issue for architects right up to the beginning of the modern period, in which a paradigm shift occurred in the perceived relationship between humans and the wider environment, and an extravagant use of resources in works of architecture was actually encouraged, facilitated by the availability of cheap hydrocarbon fuel. The resulting squandering of the planet's resources has caused the well-documented crises of climate and ecological emergency that will require that every aspect of human activity, including obviously architectural design, will have to be seriously reconsidered. I'm going to begin investigating these issues by considering the building of the Baths of Caracalla in Rome in the 3rd century CE, which was one of the largest and most complex building projects ever carried out in Roman antiquity, and indeed in any age of architecture. It presented formidable problems of structure and spatial organization, as well as in the management of resources. The building was a bathhouse, which in Roman times were centres not just for bathing, but for social activity and interactions of all kinds. The building consisted of a series of covered spaces with controlled environments ranging from hot through tepid to cold, unheated rooms, many of them provided with plunge pools. A major uncovered swimming pool and 2 exercise yards were also provided, and all of this accommodation was on a very grand scale and designed for use by large numbers of people. There was also much ancillary accommodation, such as changing rooms and rooms for the management of the hot air and water systems. The building is entered on the north side. The entrances are here. Here is the swimming pool and the frigidarium, the cool room, and the largest space in the building, leading through the tepidarium to the caldarium, the hot rooms at the south side of the building. Here is the entrance front, the swimming pool, the frigidarium, and the caldarium. And in this section, which is through the centre of line of the building, the swimming pool and the frigidarium, the cold room. Here is the frigidarium again, and here is a depiction of how it may have appeared in use, looking from the frigidarium into the swimming pool beyond. And in Alma Tadema's famous painting, an indication is given of the kinds of social activity that may have occurred. The building was located on a sloping site to allow water to flow through it by gravity. The water was introduced from an aqueduct, seen on the left here, into a series of cisterns and then flowed into the caldarium, the hot rooms, where it was heated by furnaces located in the basement. It then flowed through the tepid and cold rooms to the swimming pool and eventually into a drain. The fabric of the building consisted of a structural armature made from combinations of stone, rubble, and brick, to which a thin skin of spectacular ornamentation, principally executed in multicoloured marbles and mosaics, was applied to give a sumptuous quality to the interior. The building is remarkable for the way in which the structural requirements that had to be met to create a series of large enclosures in various types of masonry were integrated with the space planning of the building to create a sequence of visually exciting interconnected interiors, and to the attention that was paid to the careful management of resources. The requirement for a long span structure to cover the major spaces of the interior was the principal structural problem that the Roman builders had to overcome. There were 2 possibilities with which they could have achieved the required long spans. One was the use of timber trusses. The other was the use of masonry vaults or domes of some form. They opted for masonry vaulting, and this was probably because the resources of large timbers that would have been required for long-span timber structures were simply not available, or at any rate would have been very expensive. Another factor was that the principle of triangulation as a way of constructing long-span timber structures was not understood in Roman antiquity, and it is in fact questionable whether the spans required for the Baths of Caracalla could have been achieved with Roman timber technology. Here is an example of Roman timber technology, the church known as St. Paul's outside the walls. And in this roof, the structural elements that span the width of the nave are the rafters. They are carrying the weights of all the other elements in the roof, which hang from them. The principle of triangulation, in which all of the elements contribute to the spanning of a space, was not fully understood until the 19th century. An interesting fact of construction history that we do not have time to go into here. The masonry vaulting is potentially a compressive form-active structure, although the vaults which the Romans used had semicircular profiles to simplify construction, which made them semi-form-active. The primary reason for the adoption of a semi-form-active vault to achieve a long span in masonry was not so much to achieve efficiency in the use of material, which it did, as to maintain the material in a state of compression. Masonry has little strength in tension and therefore bending, so simple, non-form active structures are not an option if a long horizontal span is to be achieved. A problem with the vault and dome is that they produce horizontal thrusts which tend to push over the supporting walls. The walls of tall spaces covered by vaults or domes are in fact also semi-form active structures, subjected to a combination of bending due to the horizontal thrust from the vault and axial compression due to the weight that is carried. For a satisfactory structural performance, the walls have to be thick, so as to limit the amount of tensile bending stress that occurs and make it always less than the compressive axial stress caused by the weight of the vault that the walls carry. And if you wish to read up about this, please consult Chapter 4 in my book, Structure and Architecture. It's also described in the Structural Architects section of this website. A vaulted or domed enclosure tends therefore to have a bulky structure. Being semi-form active, both the horizontal and the vertical elements have to be thick. The Roman engineers realized that although the elements had to be thick, they did not have to be solid. The voided wall is an improved semi-form active structure. The reduction in the weight of the vault or dome by coffering was also a form of improvement. So both the vaults and the walls of the Roman vaulted enclosure are improved semi-form active structures. A further development that the Roman engineers used was the cross vault that created flat areas of wall at roof level and that were used to provide windows that admitted light into what would otherwise have been a dark interior. The shaded elements here are the structural elements, the very thick voided walls and the thick but coffered vault. And in the plan, the thick but voided semi-form active walls of the cross-vaulted frigidarium are discernible. The uncovered swimming pool has thinner walls. Virtually every aspect of the form of the structural armature of the Baths of Caracalla was therefore determined for structural reasons to maximize economy in the use of material. The resulting shapes were brilliantly exploited by the architects of the building to create an interesting architecture of the interior with sequences of interconnected spaces of varying height and size. The method of construction was also such as to make economic use of material. The way in which this complicated cross-vaulted structure was built was by constructing thin skins of brickwork, which was an expensive material, and then infilling, creating the bulk of the walls, with rubble, which was an inexpensive material both in monetary and in energy terms, as we'll see. The sumptuous interior was created by applying a very thin skin of what would have been a very expensive material, coloured marble. Although the massive remains of the structural armature of the building give the impression of extravagant or even profligate use of material, sanctioned by an emperor who wished to create a symbol of wealth and power, the building was in fact an example of the very careful use of resources. The predominant use of semi-form active elements, all of them improved by voiding, for all of the principal parts of the structural armature, meant that, considering the total area covered by the building, the quantity of material involved was in fact relatively modest. This was a primary factor in minimizing the energy that was required for its construction, its embodied energy in the terminology of the present day. This photograph shows the remains of the building in the present day. The manner in which the embodied energy was distributed in the building is of considerable interest as a demonstration of the careful way in which this was managed by the designers. It reflects the variation in the availability of various types of energy to the builders. 3 types of energy were crucial. Human energy, directly related to the number of labourers involved in constructing the building. Heat energy, the energy required for making some of the building materials, the most significant being bricks and lime, which required furnace temperatures of around 1000 degrees centigrade. This consumed large quantities of the only fuel available, charcoal. Available timber resources for making charcoal were therefore a consideration, especially as timber was used as fuel for other purposes, such as domestic heating. And then finally, transport energy, minimized by sourcing materials locally. The form adopted for the building was heavily influenced by the availability and therefore cost of these three components of embodied energy. The use of improved semi-form active forms for the principal structural elements involved geometric complexity that in turn required considerable input of labour. This form of energy was readily available in Rome at the time. The ultimate source of this energy was, of course, food, then readily available in the form of grain from Egypt. Climate was an important factor. Climate historians tell us that between 600 BCE and 300 CE, the climate of Egypt was particularly favourable for the growth of grain. Egypt was in fact the breadbasket of the Roman Empire that allowed the growth of large urban centres, of which Rome itself was the largest. This period ended with climate change that occurred naturally in the 3rd century CE. The climate became colder and less predictable, and this reduced crop yields. It has been argued that it was this that was primarily responsible for the fall of the Roman Empire, a fascinating topic that we cannot go into here. A secondary benefit of the adoption of a labour-intensive method of construction for the Baths of Caracalla was the provision of employment for the urban poor of Rome, always a concern for emperors who had to avoid social unrest as a potential threat to their power. The other two required energy inputs for transport and heat were in much shorter supply than labour energy, and the form of the building was organised to minimise the requirement for these. The energy source for transport was, of course, forage for draught animals, such as oxen. The availability of this resource, obviously related to climate and geography, will have been well understood and of immediate concern to the planners of the building. Rome was essentially an agrarian economy. Resources for draught animals for transport were limited. The bulk of the material for the building was sourced locally, from within 20 miles of Rome itself, to minimise transport costs. To minimise the heat energy required, the quantities of lime and bricks in the fabric of the building were kept as small as possible. Lime accounted for only 3.2% of the volume and bricks 2.7%. 76% of the bulk of the building consisted of stone rubble that consumed no heat energy and was sourced locally. The one serious extravagance, so far as materials were concerned, was the use of marble for ornamentation. But by confining this to a thin veneer applied to the surfaces of the structural armature, the requirement for this was minimized. Marble constituted only 0.5% of the bulk of the fabric. Thus was created a spectacular architectural monument that was produced at minimal cost so far as energy resources were concerned, and that satisfied the requirements of its builders. It provided a set of well-serviced spaces that worked well for their intended purpose. It produced a major public monument that enhanced the standing of the emperor, and it represented a careful use of available resources. It was also produced from resources that were renewable. It was also, in present-day terminology, an example of a sustainable architecture. The reason for its ruined state was not lack of durability. The building was systematically dismantled and used as a quarry for its marble finishing materials at the time of the Italian Renaissance. This fate did not befall the similar Baths of Diocletian building, which has continued in use until the present day. From the viewpoint of our own time, these buildings offer an example of how a monumental and long-term durable public building of architectural quality with highly complex programmatic functions can be created from materials and energy sources that are renewable. If in the present day we are looking for an example of how to create a major building from resources that are of low carbon footprint, durable and renewable, this is it. This is how it can be done. The Riverside Museum in Glasgow is an example of the almost complete reversal of the design methodology that was adopted for the Baths of Caracalla. In complete contrast to that building, the use of energy and material at the Riverside Museum was extravagant, largely as a consequence of the formalist approach to design that was adopted, that favoured an architectural idea that was unrelated to how the building would function or to its consequences for the consumption of resources. Whereas for the Baths of Caracalla, the overall form and general arrangement were primarily determined so as to achieve an optimum use of available resources and satisfaction of programmatic function, and the architectural quality allowed to follow from that, with the Riverside Museum, a formalist architectural idea was allowed to dominate the design. The resources required to realise the form were of secondary importance. The building has a freely determined form which, in the words of the designer Zaha Hadid, was intended, quote, to link the city and the river with fluidity that engages with its context. According to Hadid, again quote, the building combines complexity with structural integrity and material authenticity, end of quote. In view of the problems for structural design and resource management that were a direct result of the building's form, one might reasonably ask, what precisely did Hadid mean by terms like structural integrity and material authenticity? The building consists principally of a single volume gallery space that extends uninterrupted through the entire length of its S-shaped plan. From the side, the building has a rectangular elevation, but the end elevations and cross-sections have an irregularly serrated top with profiles that vary continuously along the length of the building to create a series of ridges and valleys in the roof that vary in height and width along its entire length. The problems associated with providing structural support for this geometry were formidable. Given its size, the engineers had little choice but to use a skeleton framework of steel, a material with a level of embodied carbon that is more than 20 times that of the materials from which the Baths of Caracalla were made. Due to the peculiarities of the overall form of the Riverside Museum, the general arrangement of the steel framework had to be significantly different from the practice that is standard for a single-story steel framework. The most economical arrangement for such a building is to have primary structural elements spanning in the short direction across the normally rectangular plan of the building and place these reasonably close together so as to limit the span of the secondary elements to which the cladding is attached. The structure of Foster's Thamesmead warehouse, seen here, in which semi-form active portal frame primary elements at relatively close spacing carry non-form active secondary elements, is a typical example. This type of arrangement gives best economy of means in the use of structural material. It could not be used for the Riverside building due to its configuration in plan and cross-section. The primary span direction of the Riverside building had to be longitudinal, parallel to the roof ridges, and this was accomplished with a series of triangulated girders that followed its varying longitudinal profile. Transverse structures were required to support these girders, indicated by the dashed lines here. In the glazed end walls, coloured blue, these took the form of closely spaced mullions that, in effect, made the end walls into load-bearing walls, contrary to their appearance. A complex three-dimensional framework that occupied the entire curvilinear portion of the plan was required to support the longitudinal girders through this central part of the building, indicated here by the dashed red lines. This structure operated as an amalgam of portal frame action between the columns at the edges of the plan and curved versions of the primary triangulated roof girders running through the S-shaped part of the plan. Taken as a whole, it is a semi-form-active space framework that required massive amounts of steel for adequate strength. The introduction of features that could have increased structural efficiency was unacceptable architecturally. One such feature could have been the insertion at intervals of elements that linked the tops and bottom of the roof ridges to create transverse spanning triangulated girders. These would have interrupted the roof valleys and were unacceptable for visual reasons. The introduction of columns into the single volume interior so as to reduce the spans involved would have greatly reduced the volume of structure required, and it is not clear that this would have compromised the programmatic functioning of the building. The provision of an uninterrupted space was therefore an architectural gesture rather than an operational necessity. The continuous variation in the depths and widths of the roof ridges and valleys greatly complicated the detailing of both the structure and the cladding. Ingenious solutions to this were found, but there is no doubt that this feature greatly added to the complexity of the design fabrication process and therefore to the embodied energy of the building. The building therefore has a very complex structure that was extravagant in every sense. It made an inefficient use of material, it was difficult to design and construct, and it was made in steel, a material with a very high carbon footprint. It is questionable whether the architectural benefit of the form justified this highly profligate expenditure of society's resources that was involved. The approach to design that is encapsulated in the Riverside Museum is the one that has been dominant in the entire period of modern architecture, in which the overall forms of buildings have been determined from abstract theory and virtually no regard paid to the environmental consequences of design. It is still very much alive in the present day of climate emergency. It is an approach to design that is in marked contrast to what was adopted at the Baths of Caracalla, in which the design of the building evolved from a consideration of the best way to construct it and of the most expedient use of energy and materials. An approach in the present day that favoured the idea of economy of means would be an ethical position in which designers had a moral duty not to waste society's resources on buildings that made an unnecessarily extravagant use of materials and energy. It would be in considerable contrast to the approach that has driven the modern period in architecture, in which excess and the extravagant use of energy and materials have often been regarded as virtues, necessary attributes in the creation of form that properly expressed the excitement of the age of speed, technology, and the machine, an age whose activities can now be seen as having brought the world near to a position of environmental catastrophe, a possibility to which architecture has made a significant contribution. The need to do things differently is now abundantly clear. The ability to distinguish between forms that are extravagant and those which perform with economy of means is now of paramount importance. The ideas outlined in this series of presentations have a role in this new approach to the design of buildings and other infrastructure.